Good afternoon, everybody. My name is Shubhranshu Kumar Tiwari, and I'm here to present my paper Analysis of the Employability and Benefit of the Application of Artificial Neural Net-based Monitoring System for Utility Networks. This is a brief overview of the topics that I'll go through. The revolutionary and astounding new developments in the world of computation in the last 3 decades have prompted researchers and engineers to look towards pattern recognition and machine intelligence with renewed vigor. Application of machine intelligence to any field helps to find such minutiae that are impossible to find out otherwise. Also, the speed of response for a properly trained machine intelligence unit for a pre-trained set of situations is very fast compared to the human response. In this paper, neural net models have been applied to monitor the active power flowing on the lines of the Damodar Valley Corporation's power grid network and to determine if the power flows are in a secure or insecure state. The ANN are used here in two modes, a multiple input multiple layer neural network mode to monitor all the lines using a common ANN or single ANN. So one single ANN has 56 inputs to monitor all the 56 line of the DVC46 bus system and gives an output of 0 or 1 depending upon whether the power flow is in the secure state or insecure state. And the second mode is a distributed single input small neural net to monitor each line separately from different points in the power system. So in the second mode, each line has its own neural network which gives the status of the power flow on that particular line. This work analyzes and goes through the pros and cons of both the above mentioned modules and enumerates the advantages and disadvantages of both common centralized ANN module and the distributed separate ANN modules for monitoring the DVC power system grid or any other grid for that matter. To generate the training data for a given loading condition based on day-ahead load forecast, unit commitment, and scheduling, a load flow program is run to calculate loading conditions of the transmission lines. After the line loadings are calculated, it is given a differential calculative error margin of plus minus 10% to generate the appropriate amount of training data for the ANNs that will be used for monitoring the lines of the network. So plus minus 10% margin means, say the power flow on one of the lines is 50 megawatts. So if you give a plus minus 5% or plus minus 10% margin, so it means that the power flow, if the power flow on that particular line is between 45 megawatt to 55 megawatt, is within that range, the power flow will be secure. The ANN will classify that power flow on that line within the range of 45 to 55 megawatt is secure, and the power flow beyond that range will be classified as insecure. So this is done for simplicity also because the power flow on any transmission line at any given instant is not the same as it was previously, and it varies from time to time. So for that reason we give a plus minus 10% margin. Next, we also perform contingency analysis and feed its data to the ANN so that the event of outages of any of the lines may also be detected by the ANN, and also the critical flow gates which may get overloaded during a cascade event can also be identified. The predominant problem in the traditional process of load flow method based security monitoring procedure is that it is prevalently iterative in nature. Take Newton-Raphson fast decoupled load flow or DC load flow or Gauss-Seidel load flow. They are all very computation intensive. So performing them for a small system is easy, but performing them for a larger system like DVC46 bus system or even larger 100 bus, 200 bus system in real time is very complicated and very time consuming. And it is not practical to perform it in the real time. So in that scenario, we can use an ANN. So the ANN we use here gives an output of 0 when the power flow on the lines is in a secure state, and the ANN gives an output of 1 when the power flow on the lines is in an insecure state. So this is the DVC46 bus network that I've been using for my study. As you can see, it is very complicated network and it is a very large and interconnected network. This data or this diagram, this network data was downloaded from the training report of one of the candidates of IIT Kharagpur that I found on scribit.com. So you can see from the link there. The Simulink model of the same system is developed in MATLAB. Just to get into perspective, I've shown here an IEEE 14 bus system So here you can barely make out the three-phase sources, these two, or the three-phase lines, or sorry, three-phase transmission line, bisection lines. You can barely make it out. Then you can also you can't even make out these loads. These are the loads. You can hardly identify them. You have reactive compensators. You have transformers. So the scale of the system is very large, and I have minimized it for ease of visuality in this slide. So it is very hard to make out all the blocks. Here you can see a three-phase timed fault was induced. Similarly, here also, line number 3, line number 9, and line number 25, we induced 3 different faults. So similarly, the types of ANN used for monitoring here are two types of mode as explained previously: multi-input ANN to monitor all the lines together using a common ANN, and a single input ANN to monitor all the lines using separate dedicated ANNs for each line. And when the power flow is in the line, when the power flow on the lines is in insecure state, the ANN gives an output of 0, 1 actually. And if the power flow stays in the secure and stable state, the ANN responds with an output of 0. So using the IEEE 14 bus system, I'm showing you a single common ANN. This single common ANN, or this blue square or blob, is the ANN, feed-forward backpropagation neural network model, that takes in the line power flow data of all the 20 lines of this IEEE 14 bus system as an array, and gives an output of 0 or 1 based on the state of the power flow on the lines. So here we have a separate ANN model. So here you can see active and reactive powers are being monitored by separate ANNs for the IEEE 14 bus system. So you see it is very hard to make out any blocks here. Similarly, here you have an IEEE 30 bus system model. So I don't think you can make out anything here. So the DVC46 bus system is almost twice as large as the IEEE 30 bus system. After the system was prepared on the Simulink model, after the Simulink model of the system was prepared, the simulation was performed with the help of the neural network toolbox on Simulink of MATLAB R2015A version. And this simulation was performed in real time using Opal RT's OP5600 hardware in the loop simulator that I got the permission to utilize at the Jadavpur University Electrical Engineering Department. The device had the high frequency step size of 50 microseconds, and the simulation was run in real time for a duration of 30 minutes. During the duration of the test, 3 major faults were induced on the crucial lines of the network, namely a line-to-line fault on line 3 at 10 minutes, a 3-phase to ground fault on line 9 at 18 minutes, and a 3-line fault on line 21 at 25 minutes. So this is the response of the common ANN that monitors all the lines of the DVC46 bus system. So here you see the x-axis is 0. The x-axis is actually the time, and the y-axis is the magnitude of the response of the ANN. So here you see the value is closer to 0, means the system is in a stable operational state up to 600 seconds. And at 10 minutes, a fault was induced on line number 3. Line-to-line fault was induced on line number 3. Since line number 3 is a very important and crucial line on the DVC46 bus system, so here you can see the whole operational state of the whole power network goes into an insecure state or closer to an insecure state. But as the fault is cleared, it promptly returns back to 0. Similarly, again at 1080 seconds or 18 minutes, another fault occurs, and here you can see at 1080 seconds, the ANN output goes to 1 or closer to 1, but it comes back to 0, or the power system the whole network comes to steady state after the fault is cleared. The 3-line fault on line 21 at 25 minutes does not affect the power flow on the power network as a whole, albeit there are some localized effects which die down promptly. Next we have the distributed single input small individual ANN. So the response of the separate ANN is more detailed, and the output of the ANN monitor gives the intricate insight into the behavior of the power flows on each line. Since there are 56 lines in the divisive 46 bus system, to preserve space and time, here similar types of responses have been represented under the same figure. From figure below, the NN monitoring the response of the lines getting affected by all the three faults is shown. So here you see the fault at fault on line 3 at 10 minutes, the fault on line 9 at 18 minutes, and the fault on line 25 at fault on line 21 at 25 minutes, fault on line 25 at 21 minutes is represented here. So the lines affected by these faults are line number 1, 2, 3, 4, 5, 21 and 29. Similarly, lines affected by the first two faults are represented here. The response of the ANN which respond to the first two faults. The lines which are affected by the first two faults are 6, 8, 10 and 56. Similarly, the lines affected by the last two faults are lines 17, 18 and 19 and 20. The lines affected by the first and the last faults are line 38, 43 and 44. Lines affected by the first fault only are 11 to 14. Only line 16 is affected by the second fault and line 15 is affected by the last fault. And the lines not affected by any fault are represented here. The plot of the ANN monitoring the lines not affected by any fault is shown here. So here you see the ANN output is a flat line of 0. So the power flow on these lines were not affected at all by the fault on the other lines. So from all of the above responses, it can be seen that the ANNs monitoring each line give the response of the effect of the line faults immediately. There is hardly any delay. And these kinds of prompt forewarn can allow the power system operator to take corrective actions punctually, thereby reducing the risk of uncontrolled equipment outage and by keeping the power system in a stable operational state. From the above study, the following points are concluded. The first one is the time consumption in generating ANN model. Generating separate ANN models to monitor each line separately takes more time compared to generating a common ANN model or monitoring all lines together. For example, if a bus has n number of lines and the time taken to generate each ANN model is t units, then the total time taken to generate separate ANN models is n into t, while for generating a common ANN model, the time taken is t. The second point, or the second conclusion, is it is the work involved. It is easier, faster and convenient to generate a common ANN model to monitor all the lines together, while it is rigorous and time consuming to generate separate ANN models to monitor each line separately. The third conclusion is the ANN response contrast. Although the development of a common ANN is simpler and faster, but it is very hard to identify the line on which the fault has occurred while using it for monitoring purposes. Also, the response of the common ANN is not as accurate as obligatory, but while using separate ANN models for monitoring, the ANN corresponding to the faulty line responds to the contingency immediately or the faults immediately. And the responses of the separate ANN is with much better detail and more insight into the faulty lines of than the response compared to the common ANN. The fourth point is the suitability of the ANN application. From this study, it is also observed that the application of a common ANN for monitoring all the lines is better suited and more economical for a central monitoring unit or a central load dispatch of a power system utility, while application of separate ANN models to monitor each line will be better suited and more economical for the various substations of the network or separate grid operation and management divisions. The last point that was concluded was the contingency analysis. It is easier to study contingency analysis while using separate ANNs to monitor each line, while it is very complicated, difficult and cumbersome to study contingency analysis while using a common ANN to monitor all the lines together. For future scope, automatic learning decision trees and joint ensemble of ANNs may be used to reduce the errors incurred due to human interaction during training of the ANN. That concludes my work and my presentation. These are the references that I've used for my work. That'll be all. Thank you. Please mail your queries to me at these email addresses if you have any query.